Hello. We are about to discuss one of history's quietest yet most powerful revolutions: cement. After stone, mud brick, and clay, the emergence of cement in humanity's construction journey fundamentally transformed the world. From the lime mortars of the Roman era to modern skyscrapers, this gray powder has laid not only the foundations of buildings, but of civilizations themselves. Today, it is the strength of cement that keeps our cities standing, connects our bridges, and raises our dams. Yet, with this power come profound questions. Is cement a symbol of progress or of environmental burden? Taming stone, the earliest construction materials. Throughout human history, shelter has been more than a basic need. It symbolized power, security, and control. Even when early humans took refuge in caves, their goal was to create a space isolated from nature's chaotic forces. Yet nature does not only provide shelter, it also tests it with wind, rain, and time. Humans were thus compelled to invest not just in shelter, but in permanence. The first structures were made from raw materials like stone, wood, mud, and straw. However, these materials had structural limitations. Stone was hard, but difficult to shape. Mud could be molded easily, but lacked resistance to water. And without a binding agent to hold them together, these structures had limited longevity. This necessity gave rise to humanity's first major construction revolution: the invention of binders. The aim was not only to join materials, but to create chemical interactions that would unify them into a single whole. Early binders included clay, ash, lime, and even animal byproducts. These mixtures held stones together, forming the first foundations and walls. These primitive binders can be considered ancestors of modern cement. In Mesopotamia, bitumen was used, and in Egypt, gypsum-lime mixtures helped construct pyramids. Yet these materials were vulnerable to water, limiting early civilizations to dry regions. This constraint shaped architecture itself. Dams, waterways, and harbors would only emerge much later. In short, processing stone was engineering, but binding it, that was the true revolution. Humanity began shaping construction history not when it conquered stone, but when it learned to hold it together. At this point, a new actor was about to take the stage: cement. The Roman miracle, ancient cement and durability. One turning point in construction history occurred in ancient Rome. Structures that still stand today owe their endurance not only to architectural skill, but to revolutionary material science. Romans went beyond ordinary lime mortar to develop a binder capable of hardening underwater, opus caementicium. Its most critical ingredient was pozzolana, a volcanic ash rich in silica and alumina. Mixed with limestone, it reacted with water through a hydraulic process, gradually hardening and gaining resistance to external forces. This reaction was not merely physical, it was a chemical transformation. Modern studies show that Roman concrete reorganized its internal structure over time, strengthening further through mineralization. Thus, this cement did not weaken with age. It matured geologically. Results speak for themselves. The massive dome of the Pantheon, Trajan's Forum, the arches over the Tiber River, and, most importantly, harbor structures exposed to seawater, have stood for centuries without collapse or decay. The secret lay not just in the material, but in standardization and application knowledge. Romans used different ratios for various structures, carefully monitored mixing times, and controlled curing conditions. For them, cement was not a random mixture. It was deliberate engineering. However, this revolutionary knowledge was lost with the fall of the empire. During the Middle Ages, no one could replicate Roman expertise. Buildings weakened, lifespans shortened, and structures collapsed in damp environments. This represented one of the most dramatic knowledge losses in human history. Material science was forgotten, and architecture regressed. Concrete would only be reborn after more than a millennium. From lost formula to industrial revolution, the return of modern cement. The disappearance of Rome's cement formula hindered architectural progress for centuries. During the Middle Ages, construction reverted to simple mortar mixes, incapable of producing large, durable, water-resistant structures. This stagnation ended in the late 18th century. The Industrial Revolution transformed not only machines, but also materials. In 1793, English engineer John Smeaton sought a hydraulic mortar to build the Eddystone Lighthouse. By mixing limestone with volcanic ash, he created a mortar resistant to marine conditions, marking the first technical step toward modern cement. The true revolution came in 1824 with English brickmaker Joseph Aspdin. By firing a mixture of clay and limestone at high temperatures, he produced a new binder called Portland cement, named after its resemblance to Portland stone. This invention laid the foundation for all cement used worldwide today. Portland cement offered high strength, rapid hardening, industrial-scale production, standardized ratios. With this, cement became controllable engineering material rather than artisanal craft. Concrete reinforced with steel opened the way for high-rise buildings, bridges, and large infrastructure projects. This transformation enabled the development of modern urban architecture, transportation networks, and infrastructure systems. Cement had become not just a binder, but the structural backbone of modern life. Portland cement, the birth of standards and widespread use. Joseph Aspdin's Portland cement, developed in 1824, was the first chemically defined and standardizable binder in construction history, forming the cornerstone of the modern building sector. Its production process was highly controlled. Limestone and clay were mixed in specific ratios, fired at approximately 1450 ders. The resulting clinker was finely ground into powder. Gypsum could be added to adjust setting time. This process made cement consistent, storable, and transportable, suitable for mass production, reliable across different climates. By the mid-19th century, Portland cement spread from the UK to Europe, the Americas, and the Far East. Its proliferation necessitated standardization. Mechanical strength tests, setting time measurements, chemical content inspections, water-to-cement ratio calculations. Cement became strategic, used not only in buildings, but also in dams, railway bridges, sewer systems, ports, and coastal structures. It was no longer a mere building material, but a critical factor influencing cities, economies, and even conflicts. The age of concrete, rebuilding cities with cement. Standardized Portland cement transformed construction technology. Yet the true revolutionary power lay in concrete, a combination of cement, aggregates, sand, gravel, and water. Concrete is highly compressive, moldable, producible on a large scale, and cost-effective, traits that made it the backbone of urbanization. By the late 19th century, reinforced concrete systems developed in France, using steel reinforcement to resist tension. This allowed taller buildings and larger spans, giving rise to skyscrapers, tunnels, bridges, metro systems, airports, dams. After World War II, concrete's importance surged in rebuilding European cities, while in the United States, suburban expansion made concrete essential for housing. Concrete also became an aesthetic choice. From the 1950s, modernist architecture embraced exposed concrete, symbolizing strength, simplicity, and modernity. Today, over 70% of the world's building materials by volume is concrete. Cement, the core component, is produced at roughly 4.5 billion tons per year, making it not only a technical, but a geopolitical matter. Its energy use shapes national policies, and its environmental impact influences global warming debates. In short, cement and concrete shape cities not just physically but in scale, form, speed, and cost. Hidden risks. Carbon footprint and ecological cost. Cement is indispensable. But this indispensability comes at an environmental cost. Its production involves three main stages: extraction and grinding of limestone, kiln firing at 1450 degrees C to produce clinker, grinding clinker into cement. Two major sources of carbon emissions exist: thermal energy, fuels like coal, oil derivatives, or natural gas for high temperatures; chemical reactions, heating calcium carbonate releases carbon dioxide. Cement production accounts for roughly 8% of global greenhouse gas emissions, double that of all aviation. Additional impacts include ecosystem destruction from limestone quarries, high water and energy consumption by kilns, air quality reduction from dust and gas emissions. In countries with concentrated production, e.g., China, India, limited environmental oversight worsens the impact. New approaches include alternative fuels, biomass, Waste plastics, carbon capture and storage, CCS. Supplementary materials to reduce clinker content, fly ash, silica fume, green cement, and carbon-neutral production projects. However, traditional methods still dominate worldwide. Cement persists as both a cornerstone of civilization and an invisible environmental risk. The future demands cement that is not only strong, but sustainable. Pursuit of innovation, geopolymers, carbon neutrality, and alternative cements. As environmental impacts increased, scientists and engineers focused on next-generation solutions, durable, economical, and eco-friendly binders. Three main approaches stand out. A. Geopolymer cements. Alternatives to Portland cement, using industrial waste rich in aluminum and silicon, e.g. fly ash, blast furnace slag, crushed glass. Alkali solutions like sodium hydroxide or sodium silicate serve as chemical binders. Reduces carbon emissions by up to 80%. Benefits include high early strength, chemical resistance, and impermeability. Challenges: production complexity and chemical costs. B. Carbon capture and storage, CCS. Some cement producers capture CO2 from flue gases, storing it underground or in other reservoirs. Theoretically, this could make cement plants carbon neutral. Challenges: high energy costs, ongoing maintenance, and limited adoption. C. Supplementary and hybrid cements. Natural pozzolans, fly ash, silica fume, and basalt powder reduce clinker content, lowering emissions while enhancing specific properties such as water resistance, sulfate durability, or reduced heat release. Use is increasing globally, particularly in the European Union with incentives. These solutions are vital not just for the environment, but for the long-term sustainability of construction. Successful transformation requires updated regulations, public-private collaboration, restructured supply chains, education and awareness. Global importance of cement, from economy to geopolitics. Since the Industrial Revolution, cement has been more than a material, a development indicator, an economic growth tool, and a strategic geopolitical asset. Approximately 4.5 billion tons of cement are produced globally each year, comparable to strategic resources like oil, water, and wheat. Directly linked to development. Per capita cement consumption reflects infrastructure investments, urban transformation pace, and industrial capacity. Examples: African countries, 100 kilograms year per person. Turkey, 600 to 800 kilograms year. China, up to 1,300 kilograms year. China produces 55% of the world's cement, using it to construct vast cities and anchor a construction-based economic model. Geopolitical leverage. Cement is strategic in international projects. China's Belt and Road Initiative uses Chinese cement extensively in Africa, Central Asia, and the Balkans, projecting economic and political influence. Cement factories are energy-dependent, rely on local resources, and require large land and labor, linking cement to national security planning. A giant in conflict with climate policy. Cement is among the sectors most at odds with climate goals. Countries are exploring carbon taxes on exports, including producers in carbon trading, incentives for low-carbon production. EU border carbon adjustments may create trade barriers for developing country producers. In conclusion, cement is multidimensional, with technical, economic, environmental, and political implications. Understanding it is understanding the infrastructure and future of our age. Civilization built on dust. Cement. Shaping the future. From ancient civilizations to modern metropolises, cement has been more than a binder. It embodies human engineering, economic organization, and societal imagination. Volcanic ash-lime mortars of ancient Rome have evolved into skyscraper foundations and space center floors. Every generation has rediscovered and reshaped cement according to its needs. Cement unites not just stones, but roads, dreams, and future generations. Around the world today, new cities emerge. Temporary structures rise in disaster zones. Sustainable architecture experiments with harmony with nature. At the center remains that gray powder, now expected to be not only strong, but also responsible and sustainable. The future of cement is not just more production, but doing more with less. New formulas, opening new horizons. Scientists, architects, and engineers are rewriting its destiny. By exploring the story behind this invisible giant, we are reading humanity's progress, courage, and boundless creativity. At every step along the path from stone to city, cement has been more than a material. It has been civilization's invisible architect. Witness to wars, peace and growth, this gray powder now poses a question. Will we build the future with it or beyond it?